Hello students. So something just happened. So that's why I started. So click on like button. Click on like button. So it will reach to the maximum number of students. Again, students can join. Okay. Some interruption is there. So just click on like button again. Make me to reach 100 likes. Okay. Just get to know that. So make it fast, guys. So make it fast, students. So click on. So make sure that you are like the video. I'll start the class. Let's start. So due to some interruption, so suddenly the class was disconnected. So now I'm starting again. Okay, so just click on like button. Click on like button. Click on like button. So make sure that so reaching to the target. That is start once again. Electric current. electric current. Electric current. Electric current is nothing but so just click on like button, students. So make it fast. Just click on those who are there in the live class. So just click on like button and share to everyone. Okay, so because high time for the class. Now I equal to q by t. I equal to q by t. The rate of flow of net charge through a cross-sectional area. Okay, so I equal to q by t. Again, I started the class. So click on like button, students. So fast. Click on like button. So share to everyone. So make sure that this class will reach to the everyone. This stream will reach to the everyone. Okay. So like the button, like the class. So come to the point. The rate of flow of net charge through a cross-sectional area. The rate of flow of net charge through a cross-sectional area is called electric current. I equal to q by t. So this is the average current. Now I equal to dq by dt. That is nothing but instantaneous current. Current at particular instant. Current at the particular instant, that is called instantaneous current. So 1 ampere equal to 1 coulomb per 1 second. 1 ampere equal to 1 coulomb per 1 second. SI unit of current is ampere. SI unit of charge is coulomb. SI unit of current is ampere. SI unit of charge is coulomb. SI unit of time is second. So 1 ampere is defined as 1 coulomb of charge flowing through unit cross-sectional area per second. 1 ampere is defined as 1 coulomb of charge flowing through unit cross-sectional area per second. That is called electric current. Understood or not? So I hope it is very clear. So next one, so we'll discuss about one more point. That is here within the conductor electrons are moving or not. So in the conductor electrons are moving. So charges are moving. Positive charge, negative charge, positive charge, negative charge, positive charge, negative charge. So charges are moving in the conductor. So will you say, I'll ask one question. Will you say only 1 electron flows, current is flowing? Will you say only 2 electrons flows, current is flowing? Will you say only 3 electrons flows, current is flowing? We can't say like that, right? We can't say like that. So number of charges are moving in the conductor, then only we can say current is flowing. Okay, so positive charge and negative charge both. So that's why plus or minus NE we are taking, plus or minus. So charge is quantized, Q equal to plus or minus NE. So Q is the number of charges. Q is the number of charge. Understood or not? On one electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 1 by 1.6 into 10 power minus 19. That is nothing but 1 by 1.6 into 10 power 19. So if you solve this one, you'll get 0.625 into 10 power 19. Then you'll get in 1 coulomb 6.25 into 10 power 18 electrons. Okay, so this is very, very important. In 1 coulomb 6.25 into 10 power 18 electrons are present. So these 2 points are very, very important while problem solving. So they won't give these values, you have to keep in mind. On 1 electron, 1.6 into 10 power minus 19. In 1 coulomb, 6.25 into 10 power 18 electrons. So just click on like button, guys. So make this live class to reach everyone. Okay, so share to everyone. Click on like button. Then automatically reach to the everyone. So let me reach the 100 likes and 100 shares and 100 subscribers today for this live class. Okay, so if you like the content, if you like the channel, if you like my explanation, so let me reach the target. And coming to this one, that is about average current, instantaneous current, and quantization of charge. So values, these values you have to remember. Okay, so values you have to remember. Next one we will discuss about based on magnitude and direction. Okay, so still few more points are there related to current. Okay. If charge flow is obtained, so flow of charge, you can see first point, the flow of charge can be obtained by multiplying constant current with a change in interval. So change in time. Okay. And one more point, so flow of charge. So normally current is the function of time. So T final, T initial. Okay, then I into dt. Then coming to third one, the flow of charge can be obtained by area under the IT graph, current and time graph. So here you can observe. So I is on y-axis, T on x-axis. The graph you can take here. Okay, so the graph gives the charge. Okay, the flow of charge. So flow of charge. So that is the electric current. And coming to the next one. So based on magnitude and direction, current can be divided into 2 parts. So click on like button, guys. So let me reach to the 100 likes. So today for this live stream. Okay, and share to everyone. So let me reach the target. Now you can see, based on magnitude and direction, there are 2 types. One is direct current, another one is alternative current. Okay, so both magnitude and direction. So in direct current, so magnitude and direction does not change with respect to time. Magnitude and direction does not change with respect to time. So that is called direct current. Example, cell, battery, and DC dynamo. Okay, so DC dynamo. So here in this current, magnitude and direction does not change with respect to time. That is direct current. Okay, coming to the alternative current. So both magnitude and direction changes with respect to time. Understood or not? Example, AC dynamo. AC dynamo. And one more, you can see if the charge is moving in a circular path, so with the frequency F, if the charge is moving in a circular path, so with the frequency F, current can be written Q into F. Q into F. Understood or not? Yes, actually the flow of charge. So when current will flow in the conductor, when flow of charge, okay. So charges are moving in the conductor, then only we can say current is passing. Okay, right? So now so we'll discuss about so AC current. Next drift velocity and relaxation time. Drift velocity and relaxation time. Drift velocity and relaxation time. Relaxation time. Understood or not? That is tau. So when electrons are moving in a conductor, so here it experience force. When electrons are moving in a conductor, it experience force. So current is moving like this, electrons are moving in this direction. So when electrons are moving in the conductor, it experience force, right? So that force equal to F equal to QE or EE. So when electrons are experience force, that will produce acceleration. Yes or no? So here I am in the electrical field. So I'm experiencing some force. Okay, force is nothing but some external force, external agency acting on particular body to move forward, or so to move. That's enough, right? So then, if the force is experienced, then automatically it will move. It produces acceleration. Yes, and it produces acceleration. So that is F equal to ma. So ma equal to QE equal to EE. That is equal to, so A equal to QE or E by M. Yes or no? M. Here also M. So any formula, sometimes I will give this one, right? And coming to drift velocity. So what is the drift velocity? Drift velocity is nothing but the average constant velocity. So best example, so I am taking here. Okay, so this is the conductor, electrons are moving. So this electron is moving with some velocity. Okay, so after collision again it is moving with some velocity. So it will move, it is moving, suppose some velocity, it is moving some x. After hitting, so actually this is also moving some y velocity. So after hitting this one, so this velocity reduces, then this velocity increases, then it will move, then automatically this velocity. So like that, the average constant velocity of an electrons, okay, the average constant velocity of an electrons moving in a conductor is called drift velocity. Understood or not? So next one is relaxation time. As I said, after colliding, okay, so one electron, dish, another electron, dish, another electron, dish, another electron, dish. So collisions will take place. One electron is going to hit another electron. Dish. After that, this electron will go and hit another electron. Dish. Another electron will go and hit another electron. Dish. Then, so collisions will take place. Yes or no? So the average time between one collision to another collision. Okay. The average time between two successive collisions. We can say two successive collisions means one after another. Two successive collisions. So that is called relaxation time. So denote with tau. So here a collision. So immediately after one collision, it's not going to hit another collision, right? So it will take certain time. To hit the another electron or ions in the conductor. It will take certain time. That time between two successive collisions is called relaxation time. That is called relaxation time. Okay, so just click on like button if you like the content, if you like my explanation. Okay, if you understood the concept, relaxation time. If you click on like button, then I can understand my concept is clear. I can go to the next topic like that. And one more. So you like the explanation, and one more. You understood the concept, and one more. I can go to the next topic. So this many points are there. Just click on like button. Once click on like button, then you'll get to know. Then we can go to the current and drift velocity. Current and drift velocity. Understood or not? Current and drift velocity. Current and drift velocity. Current and drift velocity. So here we'll discuss about current and drift velocity. Current and drift velocity. Current and drift velocity. Drift velocity. So here drift velocity, current I, drift velocity Vd. So this is the area of the conductor, this area of the cross section A, this area of the cross section, and this area of the cross section. Okay, so electrons are moving. Yes or no? Electrons are moving, right? So this electrons are moving with Vd. So this is Vd. And so from here to here is length. That is a displacement or distance from here. Okay, now you can observe. So V equal to L by T. That is nothing but length by time. So if you are taking magnitude, then L equal to V into T. L equal to Vd into delta T. Okay, this length is nothing but Vd into delta T. Vd into delta T. Understood or not? Now volume. So what is the volume formula? So volume is nothing this within this region. Within this region. So how much? That is length into area. That is here you can see length is what? Vd into delta T into A. That is volume. That is volume. Now number of electrons present in the particular volume. So small is an electron density. Small n is electron density. So now here n into Vd into delta T into A. Okay. Now we know charge, the flow of charge. So n Vd delta T into A into E. Okay, we know current. What is the current? So what is the current? Flow of charge. Flow of charge by time. Okay. So that is N E A V D delta T by delta T. So here delta T get cancelled. So delta T get cancelled. What is the current? I equal to N E A V D. Now what is the current density formula? What is the current density formula? Current density equal to current density equal to J. Current density J. I by A. What is I? I equal to N E A V D by A. So A get cancelled. So can we cancel A? So then what is the current density? J equal to N E A. So sorry, NEVD. NEVD. Yes or no? So NEVD. NEVD. Once again observe carefully. So this is the conductor. So this is the area of the cross section. I am taking this portion only. I am taking this portion. That is the velocity equal to displacement by time taken. Here we are taking this one. Okay, so this length. So L by T, L equal to V into T. V is nothing but drift velocity. Here, what is velocity? Drift velocity. So Vd into delta T. Vd into delta T. Understood or not? Vd into delta T. So length, that is length. Coming to volume. What is the volume? What is the volume formula? Length into area of the cross section. Length into area of the cross section. So that is L into A. So this we are taking this area of the cross section, volume. This volume we are considering within this portion. That is length into area of the cross section. So number of electrons present in the particular volume. So n into electron is small n is electron density. So n into Vd into delta T into A. So the flow of charge, quantization of charge, n Vd delta T into A. So E I equal to delta Q by delta T. Now so delta Q equal to n E A Vd delta T. So delta T get cancelled. Delta T get cancelled. Understood or not? So then I equal to NEA Vd. Now current density formula. What is the current density formula? So current density can be represented with J. That is J equal to I by A. So we know current. We know this current I equal to I by A. So A get cancelled. J equal to NEVD. Okay. So if you like this content, so click on like button. Make me to reach the target 100 likes, 100 shares and 100 subscribers for this live class. Okay, so click on like button if you like the content, if you like the explanation, if you like the channel. Okay, so coming to the next one. So Ohm's law. Ohm's law. Coming to Ohm's law. Ohm's law. Ohm's law is nothing but the potential difference. So normally you are taking here. So okay, normally you are taking the conductor. This is the conductor. So I am connecting the voltmeter across here. Now current is flowing. The potential difference. So click on like button also. The potential difference across the ends of the given metallic conductor is directly proportional to current flowing through it. The potential difference across the ends of the given metallic conductor or resistor is directly proportional to current flowing through it. Okay? Directly proportional. So V is directly proportional to I. V equal to IR. So at a constant temperature and physical conditions also same. Okay? Understood or not? So V is directly proportional to I. V equal to IR. So at a constant temperature and physical conditions also same. Physical conditions also same. Okay, so I hope it is very clear. V is directly proportional to I. V equal to IR. So now you can take this the graph. V on y axis, I on x axis. The graph is curved, so you are taking the slope. So this is the theta. Tan theta equal to r. The slope of VI graph gives straight line. The slope of VI graph gives the straight line. So just click on like button, students. So let me reach the target. 100 targets. So for this like class. So will I get one like from each and everyone to reach the target? So now you can see V equal to directly proportional to V equal to IR. So V is directly proportional at a constant temperature. At a constant temperature and physical conditions also same. So this is for ohmic conductors. Ohmic conductors. Ohmic conductors. Ohmic conductors. The conductors which obey Ohm's law, those are called ohmic conductors. And coming to the non-ohmic conductors. Non-ohmic conductors. Non-ohmic conductors. The conductor which does not obey Ohm's law, those are called non-ohmic conductors. So I am taking here, you can observe. Non-ohmic conductors. Non-ohmic conductors. Non-ohmic conductors. Students, let me reach to the target 100 likes. So for everyone. So from each and everyone, one like. Just click on like button. Then you automatically I can reach to the target immediately. Okay. Now you can see V on y-axis, I on x-axis. The graph is curved for non-ohmic conductors. So here you can observe this is V1, this one I1, this is V2, and this one is I2. Okay. So this is P and R. Now you can see. Now you can see V1 by I1 equal to R1. R1 at P. V2 by I2 equal to R2. That is at Q. But R1 is not equal to R2. R1 is not equal to R2. Ohmic conductors. Ohmic conductors. The conductors which obey Ohm's law, those are called ohmic conductors. The conductors which does not obey Ohm's law, those are called non-ohmic conductors. Non-ohmic conductors. Okay. Non-ohmic conductors. Non-ohmic conductors. Yes or no? Students, just let me know, let me reach the target 100 likes. So click on like button fast. Let me reach the target 100 likes. So for the explanation for the stream. So just here, the potential difference across the ends of the given metallic conductor, so is directly proportional to current flowing through it at a constant temperature. And physical conditions also same. V is directly proportional to I, V equal to IR. For ohmic conductors, okay. So the conductors are circuits or materials which obey Ohm's law. Those are called ohmic conductors. So you can see the graph is straight line. So starting from origin, V on y-axis, I on x-axis. So tan theta equal to R, slope of the graph, tan theta equal to R. Okay, so VI graph gives the definition of resistance. VI graph gives the definition of resistance. Resistance is nothing but the phenomena of opposing the electric current. Coming to non-ohmic conductors, the conductors which does not obey Ohm's law. The conductors are circuits or materials are resistors. Okay, so which does not obey Ohm's law, those are called non-ohmic conductors. So here, so the graph is curve, but still you can see, so this is V1 and I1, V2 and I2, V1 by I1 equal to R1, V2 by I2 equal to R2. So V1 by I1 equal to R1 at P, V2 by I2 equal to R2 at Q. Okay, but still R1 is not equal to R2. Okay, so if you like the content, if you like the explanation, click on like button. So can I get like from each and everyone those are watching? Okay, just click on like button if you like the content, if you like the channel, if you like my explanation. So that is for Ohm's law, ohmic conductors and non-ohmic conductors. Coming to the next one, that is electromotive force. Electromotive force. Electromotive force. Electromotive force. Okay. Electromotive force. Electromotive force. Okay, so here you can observe. So I am connecting the cell here. I am connecting the cell that is connected to the resistor. So positive terminal, negative terminal. When you connect a cell in the circuit or battery in the circuit, the charges are moving from positive terminal to negative terminal. Understood or not? The charges are moving from positive terminal to negative terminal. So we know that, right? So conventional current, the flow of positive charges direction is taken as direction of conventional current, and flow of electrons is known as electric current. The direction of flow of electrons is known as direction of electric current. So everything, all the points we are very clear. Now here you can observe when positive charges are moving from high potential to low potential, high potential to low potential, or positive terminal to negative terminal. So when positive charge, so positive charge at negative terminal, that is nothing but low potential. Low potential. Okay. The force which is used to move the positive charge from negative terminal to positive terminal within the cell. Okay, in the cell. The work done to bring unit positive charge from negative terminal to positive terminal are low potential to high potential. Low potential to high potential in the cell, that is called electromotive force. The work done to bring unit positive charge from negative terminal to positive terminal or low potential to high potential are the force which is used to move the positive charge from low potential to high potential or negative terminal to positive terminal, that is called electromotive force, EMF. So E equal to W by Q, equal to W by Q. Understood or not? So if you like the content, if you like the explanation, just click on like button. So I am expecting, because those who are watching, so you can understand the concept. If you understood the concept, just click on like button. Then I can go to the next one. So right. So this is about electromotive force. Next one we will discuss about resistance. Resistance and resistivity. Resistance and resistivity. Okay, let's start. Resistance and resistivity. Resistance and resistivity. Here resistance, resistance and resistivity. So resistance is nothing but the phenomena of opposing the electric current in the circuit. Resistance is nothing but the phenomena of opposing the electric current. Here, so conductors. So substances, three types: conductors, insulators, so semiconductors, and here resistor we are talking. So coming to conductors, the substances which allow the electricity to pass through it, those are called conductors. So completely it will allow. Coming to insulator, does not allow to pass through it. Coming to semiconductors, between conductors and insulators, between, okay na? So in between that the conductivity will be there. Coming to resistor, some appreciable resistance is there. Okay, so completely it won't stop, completely it won't allow, but it opposes some current. Okay, some current, and required it will be useful for utilizing. Okay, so utilizing for the device. That is a resistor. Resistor is a device which is used to oppose the electric current. Resistance is the phenomena of opposing the electric current. Here two terms are very important: a resistor and a resistance. Resistance is the phenomena of opposing the electric current. Resistance is the phenomena of opposing the electric current. Resistor is a device which is used to oppose the electric current. Resistor is a device which is used to oppose the electric current. Understood or not? So if you understood, just click on like button. If it is clear, click on like button. Then I can go to the next concepts without any concerns. Okay. So resistor is directly proportional to length of the conductor. Resistance is inversely proportional to area of the cross section. R is directly proportional to L by A. R equal to rho into L by A. So here you can observe there is one activity. So there is one activity, that is, so take a nichrome wire. So here you can observe. So I am taking this the nichrome wire. This is a nichrome wire. So you connect. So you are taking this. You connect to the circuit and identify the ammeter reading. And just take double of length of nichrome wire and observe the ammeter reading. Okay, and take same wire with area of the cross section double. So initial length. So first one, what are first case, second case, and third case. In third case, area of the cross section here length. Here length is doubled, area of the cross section is same here. So length is same. So what we consider in the first case, and area of the cross section is twice. Then you connect these three elements. Okay, nichrome wire. So nichrome wire length L, nichrome wire double length, nichrome wire twice of the area of the cross section. Then next one you take the copper wire. Okay, so like the different material you are taking. Next different material. So the last one is copper wire. You can consider copper wire and observe. Connect all these four, and all this in the four cases. Observe the reading of ammeter. That is nothing but current passing through the ammeter. Then you can observe resistance is directly proportional to length of the conductor. Resistance is inversely proportional to area of the cross section. Resistance is directly proportional to L by A. Resistance equal to rho. Okay, rho is nothing but resistivity. Understood or not? Rho is the resistivity. R is the resistance. Right? Yes. So now you can see. Okay. Now SI unit of resistance is ohm, and the symbol you can take. Resistance depends on length and area of the cross section. That is nothing but physical dimensions. And resistance depends on temperature. And coming to resistance depends on nature of the material. Understood or not? nature of the material. Is it clear? Is it clear? Just check once. Is it clear? So if you like the content, if you like the explanation, so click on like button. Okay, let me know you understood the concept. So concept is clear. Then I can go to the next one. Resistivity. So definition also I'll explain. Resistivity is equal to RA by L. RA by L. So SI unit of resistance is ohm. SI unit of area is meter square. SI unit of length is meter. Here you can observe. SI unit of resistance is ohm. SI unit of area is meter square. SI unit of length is meter. So meter get cancelled. Then resistivity equal to ohm meter. Resistivity equal to SI unit of resistivity is ohm meter. Understood or not? So we can write like this: ohm meter, and now so ohm meter like this. And coming to the resistivity depends on temperature. Resistivity depends on temperature, and resistivity depends on nature of the material. Nature of the material. Nature of the material. Understood or not? Four times. When the wire is stretched to double of its length, area of the cross section decreases. Then area rho equal to R equal to rho into L by A, 2L, A by 2. So 2 goes up, then 4 into R. So Ritesh, that is your answer, 4R. R dash equal to 4R. Okay, done. So this is about resistance and resistivity. Resistance and resistivity. So you ask the question, right? Yes, you can see. If length is L, L1 is L, L2 is twice. Okay, when length is doubled, area of the cross section is half. Then R equal to rho into 2L by A by 2. Then R equal to rho into 2 into 2L by A. Then R dash, this R dash. When you are substituting 2L, then definitely it is R dash. Then R dash equal to, so 4 into R. Is it correct? So let me know if it is correct. Okay, done. Now, so we'll go to the next one. So temperature dependence of resistance. Temperature dependence of resistance. So volume is same, right? Volume is same. But when you are stretching, automatically R is directly proportional to L, R is inversely proportional to area, right? So area it is related. So without changing the area, how can you extend? How can you stretch the wire? So I'll give one wire. So without changing the area of cross section, will you change the length? Will it is possible? So now you can see temperature dependence of resistance. Temperature dependence of resistance I'll give. Temperature dependence of resistance. I'll give two incidents. So I'll give two incidents. So when temperature increases, so two situation will happen at a time. So as soon as you increases the temperature, as soon as you increase the temperature, the free electrons in the conductor increases. So it vibrates, it moves with a greater amplitude, and ions of the conductor also moves with a greater amplitude. So when electrons are moving, then conductivity increases, resistance and resistivity decreases. Ions of the conductor moves with a greater amplitude, electrons are moving with a greater amplitude, then what happens? So conductivity increases, resistance and resistivity decreases at that particular instant. Note this point. Coming to the next point. If electrons, so normally there is so much place is there. Okay, so there is so much huge place is there. If people are running, so much place is there, they can move in different directions. But in the conductor, electrons are moving within that region. Okay, so within that particular enclosure, within the particular area, within that particular volume, then what happens? That two electrons are moving with a greater amplitude. Then what happens? One electron will hit another electron, and electrons will also hit the ions of the conductor. Yes or no? Yes or no? Then what happens? Collisions will take place. Then what happens? So resistance and resistivity increases. Electrons are colliding there itself. They are not moving forward. Then what happens? Resistance and resistivity increases. Conductivity decreases. Resistance and resistivity increases. Conductivity decreases. So that's why in the just now I wrote in the resistance and resistivity. So resistance depends on temperature. Resistivity also depends on temperature. Understood or not? Yes or no? So that's enough. If you like the content, if the concept is clear, click on like button. So let me know the concept is clear to everyone. Then I can move forward. So click on like button, then I can understand. Next one is yes. So one more point. If temperature increases, length and area of the cross section also increases, right? Length and area of the cross section of the conductor increases. Temperature increases and length and area of the cross section also increases. So till now we discussed about resistance and resistivity, conductivity, all those points we discussed. But what about length and area of the cross section? Those are also changes, but those are quite small. Okay, very less. Okay. Now you can see that is, so R is directly proportional to L, R is inversely proportional to area of the cross section. R is directly proportional to L by A, R equal to rho into L by A. R equal to rho into L by A. Understood or not? That time, so L by A is constant. These are quite small. So L by A is constant. Then R is directly proportional to rho. R is directly proportional to rho. Then we can see R T equal to R naught plus, okay, sorry, R naught equal to 1 plus alpha into T minus T naught. Then R T equal to R naught plus R naught into alpha T minus T naught. Then R naught equal to R naught plus alpha into T minus T naught. Sir, what is alpha? Alpha is nothing but temperature coefficient of resistance. Temperature RT R naught by R naught into T minus T naught. What is alpha? Alpha is the temperature coefficient of resistance. Temperature coefficient of resistance. Okay. So I hope it is very clear. If it is clear, just click on like button. So if the concept is clear, if you understood, just click on like button, let me know the concept is clear, then I can go to the next one. As I said, alpha equal to temperature coefficient of resistance. When R is directly proportional to rho, then alpha equal to rho T minus rho naught by rho naught into T minus T naught. Okay. So this is about temperature, dependence of resistance and resistivity. So now we will discuss about resistors are connected in series combination. Resistors are connected in parallel combination. Okay, so I hope so concept is clear. Concept is clear. Before going to the next concept, let me know you are very clear with the concept. How I will get to know? So just click on like button, then I can understand your concept is clear. Okay. So now we'll discuss about resistors are connected in series combination. Resistors are connected in series and resistors are connected in parallel combination. Resistors are connected in series combination. Then resistors are connected in parallel combination. Okay. Resistors are connected in series combination. Series combination. Okay, resistors are connected in series combination. So now we'll see. Okay, so now we can see 1, 2, 3. 3 resistors are connected in series combination. Yes or no? R1, R2, R3. So ammeter is connected here. Now here you can observe battery switch. So positive terminal current is passing. So across R1 I am connecting V1. Across R1 I am connecting V1. Across R2 I am connecting V2. Across R3 I am connecting V3. Okay. So throughout the circuit current is same. From Ohm's law V equal to IR. So IS equal to I1 equal to I2 equal to I3 equal to I. So because all resistors are connected in series combination, so throughout the circuit current is same. From Ohm's law V equal to IR. So Vs equal to V1 plus V2 plus V3. Then we can take IRS equal to IRS Okay, IRS equal to IR1 plus IR2 plus IR3. Okay, I am taking common. So I am taking common R1 plus R2 plus R3. So I get cancelled. RS equal to R1 plus R2 plus R3. Okay. RS equal to R1 plus R2 plus R3. If n number of resistors are connected in series combination, RS equal to NR. RS equal to NR. If n number of resistors are connected in series combination, RS equal to NR. So if the concept is clear, just click on like button. Okay, so I have to reach 100 target today. So let me reach the target with the help of you. So make sure that those who understood the concept, those who got the concept, just click on like button. So next one we'll go to the resistors are connected in parallel combination. Resistors are connected in parallel combination. Resistors are connected in parallel combination. So now resistors are connected in parallel combination. Resistors are connected in parallel combination. Here you can observe 1, 2, 3. So here I am connecting So now resistors are connected in parallel combination. Resistors are connected in parallel combination. So now you can see here potential difference is same, that is Vp equal to V1 equal to V2 equal to V3 equal to V. Potential difference is same. From Ohm's law, V equal to IR. So I equal to V by R. So current is dividing, right? Current I1 through R1, I1 through R2, I2 through R3, I3. But here you can observe potential difference is same throughout all resistors R1, R2, R3. Now IP equal to I1 plus I2 plus I3. That is nothing but V by RP equal to V by R1 plus V by R2 plus V by R3. That is, V I am taking common 1 by RP equal to V I am taking 1 by R1 plus 1 by R2 plus 1 by R3. Then V will get cancelled. So 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. Then if n number of resistors are connected in parallel combination, so 1 by Rp equal to n by R, then Rp equal to R by n. Rp equal to R by n. Understood or not? So if you like the content, so just click on like button. If you like the content, if you like the channel, if you like my explanation, so if concept is clear, whatever I explained, that concept is clear, just click on like button. So let me be clear, so I can, so just click on like button, just check once. Yeah, so that is true for n number of resistors. So actually, you can see, so n number of resistors, 1 by Rp equal to n by R. But I took Rp, right? Rp. 1 by Rp equal to n by R only. That is true. But so generally we do mistake in that only. So generally people do is mistake. So until here you got some value, that only will substitute in the place of R. But actually we want Rp. That is R by N. So very simple now. So just now, till now I explained that only. So if you like the content, if you like the channel, so click on like button. Click on like button. Still I have to reach so the target. So 100 likes and 100 shares and 100 subscribers. So make me to reach. So be in that. Okay. So thank you so much. Thank you so much to all of you. So let me reach the target today. So just check once. Check once. Okay. So here resistors are connected in parallel combination completed. Now we'll discuss about Kirchhoff laws. Kirchhoff laws. Kirchhoff laws. Kirchhoff laws. Okay, so let's start. So many circuits cannot reduce into simple series and parallel. Many circuits cannot reduce into simple series and parallel. Okay. Series and parallel. So that's why we will use Kirchhoff laws. Kirchhoff laws. Kirchhoff laws. Okay. Yes. Kirchhoff laws. Kirchhoff laws. Okay, here 2 points are there. One is junction law, another one is loop law. One is junction law, second one is loop law. Junction law, second one is loop law. Loop law. Junction law is nothing but the algebraic sum of all the currents reaching at a junction is equal to 0. Okay, so I am considering here this is a 1, 2, 3, 4. This is I1, I2, and this is I3 and I4. Okay, so I1 plus I2 equal to I3 plus I4. Sum of the currents reaching to the junction is equal to sum of the currents leaving from the junction, or algebraic sum of all the currents reaching at a junction equal to 0. Okay, coming to loop law, so we can also write say sigma I equal to 0. Algebraic sum. Coming to loop law, so here 4 points are there, so observe carefully. So I am taking the cell, so this is the A and B, so positive terminal, negative terminal. So we are taking the path, this is the path. So then the EMF of this cell is positive, so negative, because we are moving from positive to negative. Coming to the second one, so this is negative to positive, we are moving negative to positive. So A and B, so negative to positive, we are this is the path. The EMF of this cell is positive, because so the final point which you are reaching, that is very important. So here negative to positive you are going, so positive EMF, you are positive to negative you are going, negative EMF. Coming to the third one, so this is the resistor point A and this one is the point B. Okay, so you are moving along the current direction, resistor. If you are moving along the current direction, the voltage V equal decrease in potential, V equal to minus IR. And coming to fourth one, that is fourth one you can see here. Now, so this is the point A to B. So we are moving opposite to the current direction R. Then V equal to positive IR. Positive IR. Understood, Anna? So these points are very, very important. These points are very, very important. Okay, so junction law and loop law. So if you understood the concept, if the concept is clear, if the laws are clear, just click on like button. Okay. So this is about junction law and loop law. And coming to internal resistance and heating effect of electric current. Internal resistance and heating effect of electric current. Okay, so when electrolyte, so we'll discuss about one more point, that is internal resistance, internal resistance, internal resistance. Internal resistance. So here, so if you are moving across the cell, so through the cell, positive terminal to negative terminal. So final point is reaching. So here, so this is the cell, positive, negative. So you are moving, this is the path, positive terminal, negative terminal. If you are moving to negative terminal, the EMF is negative. Point number one. Coming to the point number two. So if you are moving, so negative to positive, this is the path. So you are moving to the end point, that is positive EMF. EMF is positive. So you are moving from negative to positive like this. So you have to take end point, that is positive. So positive EMF. Here you are moving from positive to negative. End point is negative. So that's why negative EMF. So EMF is negative. Coming to third one, if you are moving through the resistor, across the resistor, so along the current direction you are moving. So this is the resistance and current along the current direction. So this path is very, very important. So here also path is very important. So in which direction you are moving, that is very, very important. Okay, so if you are moving along this direction, the IR term, potential, decreasing potential, that is, so minus IR. Coming to the fourth one, if you are moving opposite to the current direction, this is the current. Okay, so this is the path. I said path is very important. So you are moving opposite to the current direction. So V equal to plus IR. V equal to plus IR. Understood or not? So I hope it is very clear. Just check once. I'll be coming. Okay. So I hope it is very clear. So this is about loop law. So if it is clear, just click on like button. Right. Next one. So EMF, internal resistance and EMF of the cell. Internal resistance and EMF. Internal resistance and EMF. So when electron is moving through the conductor, especially through When electron is passing through the electrolyte, it experiences some resistance. So if electrons are moving, so it opposing, then current flow is decreasing. So that is voltage drop. Yes or no? So that is EMF. So EMF negative, EMF E minus IR. So here this is the cell, this is the internal resistance R. You are moving positive to negative. This is the path along the current direction you are moving. So V equal to, so negative to positive you are moving. So E, so along the current direction you are moving. So IR. Understood? V equal to IR. V equal to IR. Is it clear? So internal resistance and potential difference. Now we'll discuss about heating effect of electric current. Heating effect of electric current. So very important, heating effect of electric current. So just check once. Heating effects of electric current. Electric current. Heating effect of electric current. Now you can see, we know work done. What is the work done formula? So W by Q. Work done to bring unit positive charge. Work done to bring unit positive charge from one point to another point within the conductor. V equal to W by Q. W by Q. So we know, so W equal to cross multiply, W equal to V into Q. W equal to V into Q. So we know Q by T is current, right? Rate of flow of charge. So power equal to rate of doing work. What is the power formula? Rate of doing work. Then VQ by T. So P equal to V into Q by T is current. VI. So then energy E equal to P into T. Then VI into T. So H equal to, here you can see whatever the energy is given to the conductor, that will be converted in the form of heat. So V equal to IR. So voltage equal to, so V equal to IR we can take. Then IR into I into T. Then we can take H equal to I square RT. Understood or not? So check once. So potential difference, V equal to W by Q. W equal to VQ. So Q by T is current. Q by T is the current. So W equal to VQ. So power equal to rate of doing work. So W equal to VQ by T. So here we can take Q by T is I. So whatever the energy is given to the conductor, so that will be equal to P into T. P equal to VI. V equal to IR. Then so substitute in the place of VIR. H equal to IR into I into T, I square RT. So heat produced in the conductor is directly proportional to time. Heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to time. Okay, that is about heating effect of electric current. Okay, so that's enough. So thank you so much for joining and attending and listening, and so giving an opportunity to teach. Thank you so much. This is your Siva sir. If you like the content, if you like the channel, if you like my explanation, do like, share and subscribe to Student the Brand. So share to everyone, ask your friends to join to the class. Still one more topic is there, that is cells, grouping of cells, that we'll discuss in the next class. So we'll see you in the next class. Signing off. Thank you.